Under general anesthetic, you do not sleep and you do not lose time. You lie back on a cold surgical table, breathe through a rubber mask, or feel a sudden icy sting traveling up your arm, and within seconds, your entire subjective universe vanishes without a single dream or sensation. When you wake up hours later, it does not feel like you rested. It feels as though the universe paused, snipped out a piece of your timeline, and glued the edges back together. Something far more specific and profound is happening inside your nervous system. And after nearly 2 centuries of daily clinical use, neuroscience is only now discovering what was actually taken from you. It is not sleep. You have probably been told that surgery will put you to sleep. Anesthesiologists say it to calm your pulse, and your family repeats it in the waiting room. But the moment those drugs enter your bloodstream, what happens to your brain bears almost zero biological relationship to natural slumber. When you fall asleep in your bed, your brain embarks on a rhythmic, highly coordinated symphony. You cycle continuously through light sleep, deep, slow-wave oscillations, and rapid eye movement, where your cortex lights up with vivid dreams and memory consolidation. Crucially, natural sleep is instantly reversible. If someone shakes your shoulder, calls your name, or shines a bright light across your eyelids, your thalamus routes the sensory signal straight to your cerebral cortex, and you snap back to conscious wakefulness in a fraction of a second. General anesthesia is not a deeper version of sleep. It is a drug-induced, reversible coma. In a landmark 2010 paper in the New England Journal of Medicine, neuroscientists Emory Brown, Ralph Lydic, and Nicholas Schiff mapped the electroencephalogram signatures of anesthetized patients against every known stage of natural sleep. The waveforms do not match. The electrical rhythms produced by drugs like propofol and sevoflurane resemble deep hypothermia, drug overdose, and severe metabolic encephalopathy far more than anything your body produces on its own. If a surgeon cuts into your tissue during natural sleep, you wake instantly from the surge of pain. Under general anesthesia, sensory signals still travel up your spinal cord and hit subcortical structures, but you cannot be roused by pain, shouting, or physical shaking. The ancient arousal circuits in your brainstem that maintain your basic presence in the world are pharmacologically disconnected from the higher centers that generate experience. You are not resting, repairing tissues, or dreaming. Your conscious self has been systematically evicted from the control room. And as the anesthetic concentration in your brain continues to climb, the electrical storm inside your head begins to break apart into something even more unnatural. Burst suppression. As the surgical team deepens your state, the electrical rhythm of your brain undergoes a radical transformation that almost never happens in healthy human life. If you were looking at the live intraoperative electroencephalogram monitor mounted beside your bed, you would watch your normal, chaotic brainwaves slow down into dense, high-voltage waves. Then, quite suddenly, the signal changes into a pattern called burst suppression. For a few seconds, your neurons fire in a sharp, synchronized spasm of electrical energy. Then, everything abruptly drops into a flat, horizontal line of near-total electrical silence. For seconds at a time, the outer mantle of your brain produces almost no readable electrical activity whatsoever, only to suddenly flare up with another brief burst before plunging straight back into flatline silence. In clinical neurology, a flatline electroencephalogram is a terrifying marker of brain death, severe hypothermia, or catastrophic trauma. Yet, in an operating theater, anesthesiologists deliberately push your brain into this fragmented state every single day to ensure your conscious mind is completely extinguished. During burst suppression, the metabolic demand of your cortical neurons drops by up to 50%. Your brain is consuming barely enough oxygen and glucose to keep its basic cellular membranes from collapsing. Individual clusters of neurons are still physically alive and capable of firing, but they have lost the metabolic energy required to sustain a continuous narrative. Your thoughts cannot form because there is no continuous medium for them to travel through. Experience is chopped into isolated islands of electricity, separated by expanses of nothingness. You exist in an engineered state that sits on the knife edge between reversible unconsciousness and biological death. But this raises a profound question that puzzled researchers for decades. If individual neurons are still firing during surgery, why do you feel absolutely nothing? The answer lies not in whether your brain cells are active, but in whether they can still talk to each other. The integration collapse. For over a century, scientists assumed that anesthetics worked like a master power switch, simply turning off the lights in your cerebral cortex until you faded out. But modern functional brain imaging revealed something that completely overturned that assumption. When you are deeply anesthetized, vast regions of your brain are not switched off at all. Your visual cortex can still process flashes of light entering your closed eyelids. Your auditory cortex still responds to the hum of the operating theater instruments, and primary sensory regions still register the physical stimuli around you. The neurons are firing, consuming glucose, and generating electrical potentials. Yet you experience absolute nothingness. You do not hear the clatter of metal tools, and you do not see the bright surgical lights beaming down above your face. In a groundbreaking science paper by Christopher Alkire, Anthony Hudetz, and Giulio Tononi, researchers discovered that consciousness does not depend on raw brain activity. It depends on long-range integration. In your normal waking life, when you look at a red apple, one part of your brain processes its crimson color, another calculates its spherical shape, another accesses your memory of what apples taste like, and prefrontal networks bind all of these streams into a single, unified moment of awareness. You do not experience color and shape separately. You experience an integrated object. Anesthetic molecules target specific receptors, particularly gamma-aminobutyric acid pathways, disrupting the long-range feedback loops that connect distant cortical areas. Sensory information can still enter the front door of your brain, but it is instantly trapped in isolated silos. The back of your brain cannot whisper to the front, and the left hemisphere cannot share its state with the right. The moment that global integration collapses, your subjective awareness does not dim slowly like a sunset. It vanishes entirely. Your brain has been fractured into 100 disconnected processors, none of which knows the others exist. To prove this integration theory in living patients, neuroscientists had to invent a way to ping the human brain like a sonar system. The echo test. Imagine standing inside a vast cathedral and striking a massive bronze bell with a hammer. If the cathedral is open and structurally intact, the sound wave will bounce off the stone pillars, reverberate through the high arches, and produce a rich, complex, lingering echo that evolves over several seconds. But if you filled that same cathedral with thick soundproofing foam, striking the bell would produce nothing more than a dull, localized thud that dies the millisecond it begins. In 2013, A team of neuroscientists led by Marcello Casali published a revolutionary technique in Science Translational Medicine that does exactly this to your brain, creating what is known as the Perturbational Complexity Index. While you lie on the operating table, researchers place a powerful transcranial magnetic stimulation coil against your scalp and fire a painless, microsecond pulse of magnetic energy directly into your cerebral cortex. Simultaneously, a high-density cap of recording electrodes measures the electrical echo spreading across your skull. When you are awake and aware, that single magnetic zap triggers a cascade of complex, shifting electrical waves that travel across different cortical lobes, reverberating back and forth for hundreds of milliseconds as your integrated neural networks process the disturbance. But the moment you slip under general anesthesia or enter the deepest stages of dreamless sleep, the response completely collapses. The magnetic pulse produces a simple, high-amplitude spike directly underneath the coil that immediately flatlines without spreading. The echo has vanished. The Perturbational Complexity Index can calculate a precise mathematical score for your consciousness, reliably separating awake patients from those under anesthesia, deep sleep, or vegetative states. It proves that your awareness is a fragile, global resonance, an ongoing echo chamber that requires thousands of miles of axonal wiring to sustain itself. Yet even with these advanced tools monitoring your brain, the line between reversible oblivion and waking paralysis is far thinner than most patients realize. Intraoperative awareness. When you undergo major surgery, you are not given a single drug. You are given a carefully balanced cocktail of distinct pharmacological agents. One drug relieves pain. Another induces amnesia, another maintains unconsciousness, and another, known as a neuromuscular blocking agent, completely paralyzes every voluntary muscle in your body. This paralytic is essential because it prevents your diaphragm from resisting the mechanical ventilator and stops your limbs from twitching under the scalpel. But this chemical division creates a chilling clinical vulnerability. The drug that paralyzes your muscles has no effect on your consciousness, and the drug that extinguishes your consciousness has no effect on your muscles. If the anesthetic delivery falls slightly below the required concentration, while the paralytic remains at full strength, something extraordinary occurs. Your mind can wake up while your body remains completely trapped. In a landmark multi-center study published in Anesthesia and Analgesia by Peter Siebel and colleagues, researchers found that unintended intraoperative awareness occurs in roughly 1 to 2 out of every 1,000 general anesthesia procedures. In high-risk surgeries involving severe trauma or emergency cardiac interventions, where anesthetic doses must be kept minimal to protect fragile blood pressure, the incidence can rise further. In research settings, using what is called the isolated forearm technique, an inflatable cuff is placed on the patient's arm before the paralytic is injected, preventing the neuromuscular blocker from reaching that single hand. When researchers spoke to these patients during surgery and asked them to squeeze a hand if they were aware, a startling number responded by squeezing, despite showing no external changes in their heart rate or blood pressure. You could be entirely awake, hearing the voices of the surgical team and the rhythm of the monitors, unable to blink an eyelid, open your vocal cords, or draw a breath on your own. It demonstrates that the bridge between your inner subjective experience and your physical interface with the world is not an indivisible whole, but two separate chemical switches that can be flipped independently. And even when your consciousness is successfully put under, the chemical aftermath of surgery can leave a lingering mark on how your brain functions for months afterward. The recovery fog. In the days and weeks after waking from a major operation, you might assume that as soon as the drugs clear your liver and kidneys, your cognitive faculties immediately return to their baseline. But for thousands of patients every year, particularly older adults, the return to mental clarity is neither quick nor guaranteed. You might find yourself struggling to recall familiar names, losing your train of thought in the middle of a sentence, or feeling like your working memory has been wrapped in a dense, persistent haze. This clinical condition is known as postoperative cognitive dysfunction, and in a foundational international study published in The Lancet by Jan Mahler and the ISPOCD-1 investigative team, measurable cognitive deficits were documented in nearly 26% of elderly patients 1 week after surgery, with nearly 10% still exhibiting significant impairments 3 months later. Yet here is the crucial dispute that researchers are actively debating today. Science does not agree on whether the anesthetic drugs themselves are responsible. For years, it was widely claimed that anesthetic agents directly damage aging neurons or trigger neurodegenerative cascades. But rigorous modern trials have revealed a far more complex reality. When your tissue is cut, your immune system launches a massive, whole-body inflammatory response. Pro-inflammatory cytokines flood your bloodstream, cross the blood-brain barrier, and trigger microglial activation in the hippocampus, the very structure responsible for consolidating new memories. Furthermore, microemboli, subtle drops in blood pressure during surgery, disturbed sleep architecture in hospital wards, and the severe physiological stress of physical trauma all produce identical cognitive disruptions. Disentangling the chemical influence of the anesthetic from the violent biological shock of the surgical procedure itself has proven extraordinarily difficult. What is clear, however, is that your cognitive stability is far more vulnerable to systemic physiological disruption than you ever realized. And this vulnerability leads directly to the single most mysterious aspect of the entire anesthetic experience. What actually happens to the time that disappeared? The missing time. When you wake up in the morning after 8 hours of natural sleep, you retain an intuitive, somatic sense that time has passed. Even if you cannot recall a single dream, your body registers a felt duration. You know you were somewhere in the dark, resting across an expanse of hours. But when you awaken from general anesthesia, you do not feel a duration at all. You remember looking up at the round, metallic operating lights, hearing the anesthesiologist tell you to take 3 deep breaths, and then, without a millisecond of intermediate darkness or dream, you are looking at a different ceiling in the recovery room. 4, 6, or 8 hours of physical surgery have passed, but subjectively, the 2 moments are fused directly together, like adjacent frames in a film strip, where the middle scene was cleanly cut away. In clinical neurology, this profound absence reveals something fundamental about the architecture of your mind. Under deep anesthesia, you do not experience a black void, because experiencing a void still requires a conscious observer to register the darkness. You do not wait in silence, because waiting requires a continuous neural clock to measure the interval. Instead, the molecular mechanisms that encode new memories, the neural networks that generate the sensation of time, and the global integration circuits that produce consciousness are extinguished at the exact same millisecond. They are not separate mental gears working in tandem. They are the exact same biological process, observed from different perspectives. When your long-range cortical integration breaks down, time does not flow past an empty vessel. The vessel itself ceases to exist. Natural sleep gives you a gap that you can feel. Anesthesia gives you an edit. And the fact that an edit of your continuous conscious timeline is possible at all is the most unsettling thing modern medicine knows about your mind.
If this one landed, there's a companion to it. Same idea, taken somewhere stranger. It's on screen now.